Hello, Mr. Luong. This is Marla Trin in Period 1 AP Physics C. This is my take-home FRQ, Part 2, analyzing this diagram. Part A is asking for the free body diagram of both masses in the system. Hanging mass H has two forces acting on it, F of G and tension. Tension is smaller than F of G and will appear so. Block S only has one force acting on it, and that is tension. There's nothing pulling against it. This initial diagram is frictionless, one force shown as so. Question B is asking for the acceleration of H, a formula of it, for the initial system. We can start by showing that A of H is equal to the A of the system, which is equal to just A to make our work cleaner. There is a single acceleration running through the system. There's no variation in acceleration, so we don't need a subscript for acceleration. Net force is equal to the m of the system, the total mass of both of those blocks, times A. Isolating for A, we get A equals net force over m system. Because there are two forces in the system, as shown in our free body diagrams, there is T and F, but T, being an internal force, will cancel itself out. So F of G is the only part left over. So F net, the combined F, is equal to F of G, and M system is equal to the big mass, the big M plus the little m, because the pulley is massless and whatnot. There are only two masses in the system and will look like this. So ultimately, F of G over large M plus little m equals A for the system. Part C is asking for us to derive an equation for tension using the variables m, g, and A. We know from this that F of G minus T equals 2 m, the little m, times A. That is the net force acting on mass H, equaling the mass of mass H, which is little m, times the acceleration. Isolating for T, we get F of G minus ma equals T. We add T to both sides, and we subtract ma from both sides. We get this. F of G we can break up into m times G. It's the little m again, because that is the mass of hanging block H, minus ma equals T. Simplifying our math a bit, we get m times G minus A equals T. Part D is asking for what will happen when we increase the block of the larger mass and what effect it will have on the acceleration and the tension. We can start with the equation for acceleration, mg over large M plus m equals A. We can limit out large M to infinity. As the large M approaches infinity, this bottom, the denominator of the equation, will approach infinity. And infinity over mg, a constant, will equal 0, which still equals a. So a approaches 0 as the large M gets bigger. A will get smaller as the large M gets bigger. And looking into our tension equation, T equals M times G minus A. If A approaches 0, T equals mg. So as the large M increases, A approaches 0, and tension will approach gravity. Next up, looking at a slightly different system, is part E. This time, there's friction, and part E is asking for us to derive an expression for the acceleration of the system in terms of little m, large M, mu k, and g. We have up here the fact that A equals the total force on the system over the mass of the system. Let's write that down here. Now we have the M system stays the same because the masses do not change, meaning we can carry down this M system equation here. And net force changes because now there's friction. So there is mg still, which is the force of gravity acting downwards, and you have against it F of k. To define Fk equals mu k times Fn. And we know that the block on the table is only moving horizontally. So we can define the fact, we can prove that Fn equals F of g. F of g then equals m times g. So plugging that back into our equation, total force equal to mg minus mg. This is the large M, of course. mg mu k. And the final equation for acceleration of this system will be mg minus large mg mu k all over m plus large M plus little m here. Part F is asking for the equation of the tension equation using little m, big M, mu k, and g. So we can start by showing that F of the large M, the total net force acting on F large M is equal to tension minus Fk. There's one force pulling it, and Fk is acting against that force, so it will appear so. Isolating for and this equals large M times the acceleration of the system. Isolating for f of k, we add f of k to both sides. Isolating for t, we add f of k to both sides. T equals ma plus fk here. And we have already shown up here that f of k equals mu k fn. which is mu k Fg mg. So tension equals m times acceleration, which is shown up here, mg minus large mg mu k over m plus little m. And then we add f of k, which we have shown up here, mg mu k, big mg, k, to get a slightly messy equation for t. And the last part for this particular graph or diagram is part C, asking for what will happen, or it's asking us to compare the tension in this diagram compared to the tension in this diagram. Write down part C here. In the first diagram, drawn in a simplified form without the pulley, f of g is pulling this way, leaving t, but there's nothing acting against it. T is the resultant internal force of this, so pulling against it, there's nothing on this side. T is only reacting to f of g. In the second system, we now have f of k and f of g. I should probably write the masses of these blocks. We have f of k times f of g, and because tension is a reacting force, it's the internal force, and it's responding to these, it's going to be larger because there are more forces acting on the rope, creating a larger tension because they're pulling against each other. Moving on to H. Draw and label a free body diagram for all these blocks, for all 3 blocks in this system. For block, the 3 blocks are going to be large M, and then the sliding little m, m subscript s, and then the hanging m, which is going to be m subscript h. Large M has tension pulling it. It has friction acting against it slightly, and it has an even smaller contact force acting against it. So it can be written as K F little m onto big M and T. Little m subscript s has a frictional force acting against it. This is Fk big M, so this will be Fk little m, and it also has contact force pulling it, which will be F big M little m. And the hanging mass H still only has 2 forces acting against it, tension and gravity. Moving on to part I, we can see, we've already shown, that A will equal to the net force of the system over the mass of the system. Mass of the system, since there are now 3 boxes, it will be equals to big M plus 2 little m, because we know this is a single mass and these two masses are equal. Net force will be equal to F of t minus F big M K, the friction acting against the big M, and minus F little m K, the friction acting against this guy. The internal forces, the contact forces moving the blocks, cancel each other out. So this is all we're going to be left with. F of g still equals little m times gravity. F big M K is the same as the F of K from the previous times, so it equals big M G mu K. And FMK, following the same logic as our other frictional force proof back here, Fn will equal mg because they're not moving, and F of k equals mu of k times Fn. So F little m k will equal 2 little m times g times mu k. Those are components, and we can plug them back into this equation. A system A. Simplifying the math, we can get mg minus g mu k times big M plus little m over m plus 2 little m equals to acceleration, and we are given the values. Big M equals 2, little m equals 3, and mu k equals 0.18. Plugging these numbers into this equation gets A equals 3 times 9.8 minus 9.8 times 0.18 times 2 plus 3 all over 2 plus 2 times 3. And plugging this into a calculator gets the value 2.5725, which is in the unit meters per second squared because of gravity, because it's acceleration, and this is going to be positive. Next up, we have part J, which is asking for the tension in the string. We're going to start J with the net force acting on the hanging mass, which will equal the F little m g, it's force of gravity, minus HMHG, because it's the hanging mass, minus tension, which will also equal to little m times A of the system. To isolate for t, you add it to both sides and you subtract ma from both sides. Get F mHg minus ma equals t. We know this will just equal to mg. Subtract ma to get t. We have little m as equaling 3 for the system times 9.8 minus 3 times the acceleration, which we found to be 2.5725 equals t, which when we plug into a calculator, we get t equals 21.6825 newtons. Moving on to part K, calculate the contact force between block big M and block little m on the sliding section. We can start this by defining the net force of little m s, which will equal T. Let's move this somewhere else. K. The net force on little m s will equal to tension. Oh, no. This is going to be big M, the sliding one, which doesn't need a... Let's try again. K, net force acting on M, will equal to T minus the frictional force minus the contact force, m, little m, which will also equal ma. Isolate the contact force by adding it to both sides and subtracting ma from both sides to get T minus F of K for the large block minus big M A will equal Fm little m here. We know tension as being 21.6825 minus F big MK, which we defined up here in J. No. Defined way back here as being mg mu k. So big mg mu k minus m times the acceleration, which we have as 2.5725, all to equal the contact force. Big M is 2 in this diagram, so 21.6825 minus 2 times 9.8 times mu k, which is 0.18, minus 2 times 2.5725 in a calculator will equal to 13.0095 newtons. Part L is asking for the final speed of the block once it hits the ground. The system is starting at rest, so VI equals 0. It's also asking for the absolute value of V final, and we know in this system A is a constant. applied to the whole system. So there's a single A. Under these conditions, we can use our kinematics common form, VF squared minus VI squared over 2A equals delta X. We know that delta X is equal to 20, or delta Y is equal to 20. And we know that A is equal to 2.5725. If VI is 0, we can ignore this term. So VF squared over 2A equals delta Y. To isolate for VF, we multiply 2A to both sides and square root it, which will look like this. VF equals to the square root of delta Y 2A. Plugging all these into the equation, get the square root of 20 times 2 times 2.5725 is equal to VF. And plugging in this into a calculator, we get VF equals 10.14396 meters per second. Because that's what it's asking for, the absolute value. And finally, part M is asking for the time it takes to cover this distance. We can start with the equation T equals delta V over A, and this is derived from the acceleration equation A equals delta V over T. Cross multiplying will earn you this equation. We know that delta V equals VF minus VI, and the system starts at rest. So delta V equals VF. T will equal VF over A. We have VF defined up here, and we have A already solved. Plugging these values into a calculator, the value is 10.14396 over 2.5725. Plugging that into a calculator gets us 3.9432 seconds. And finally, part N is asking for the position time graph, which will look like this, the velocity time graph, which will look like this, the acceleration time graph, which is A, T, and the force time graph, net force time graph. Because acceleration is a constant in this, we can use a very basic quadratic function that we know for position. If A is constant, we know the position will look like this. We know V of t then will equal this because it's going up at a constant rate. Acceleration is a single constant, which we have up here. And force, if acceleration is constant, mass doesn't change, so it will also be a constant. And that is take home FRQ 2 complete.